Have you ever wondered what would happen if the geomagnetic North and South Pole switched places on Earth? Well, this event has occurred in the past and may happen again soon, according to scientists. There are some indications that this process may already be underway. However, such a pole reversal would have significant consequences. One major consequence would be the disruption of migratory patterns for birds. With the magnetic field shifting, these birds could lose their ability to navigate and find their way during long journeys. Additionally, the increased exposure to harmful radiation due to the shrinking magnetic field could lead to higher cancer rates in humans. Furthermore, the effects of a pole reversal could also lead to widespread blackouts in cities. Why does this happen? The Earth's magnetic field acts as a shield protecting us from solar particles. However, during a pole reversal, this protective shield diminishes. As a result, we would be exposed to more dangerous radiation affecting our skin, satellites in orbit, and even our everyday devices, such as light bulbs. Now, you might be wondering if we should be concerned about these potential consequences. To learn more about the topic and find out if we should worry, be sure to watch the video. Dynamo effect. Imagine the Earth like a giant magnet with a magnetic field around it. This invisible force helps compass needles point north and protects our planet from harmful solar winds. Now, here's the interesting part. Not every planet gets to have this magnetic field party. Why? Well, it depends on what's happening in their cores. For a planet to have a magnetic field, it needs a few things: a molten, conductive, electricity-friendly core, and some motion. Earth. This outer core with its molten iron dance is perfect for this. However, not all planets have the right conditions. Some planets, like Mars, have solid cores or cores that don't move much. The effect for which a magnetic field is created in the presence of moving electrical currents is known in physics as the dynamo effect. It is a process that is used in wind turbines or to light up your bike's headline as you pedal. It also takes place in the outer core of the Earth, where the molten iron and nickel are like busy dancers moving around. As these metals flow and swirl, they generate electric currents. Now, according to the dynamo theory, these electric currents create the magnetic field that surrounds our planet. Think of it like a magical dance floor where the metals are the dancers, and the magnetic field is the invisible dance that they create. This dynamo dance is what makes our compass needles point north and keeps us safe from the solar winds. Earth is special. It has the perfect setup for the dynamo dance and the magnetic field that comes with it. Understanding the dynamo phenomenon not only explains why Earth has a magnetic field, but also helps us appreciate the uniqueness of our planet. Now, the interesting part is that this magnetic field isn't fixed. It can change over a very long time. Yes, the flow of mountain iron changes. It's like a gigantic conveyor belt beneath the Earth's surface. When it shifts, it can influence the magnetic field. If the movements are significant, but fair enough, they can lead to a complete flip-flop of the magnetic poles, what we call a magnetic pole reversal. Scientists have been studying the change of the North Pole position over time. Their first available data goes back to 1840, when the North Pole was located in Canada. Can you believe it? As time passed by, the North Pole changed its position, and now it is located where we all know it. On average, it moves about 621 miles or 1,000 kilometers every year. But was this a coincidence? Is it just a wobble in the magnetic field? Or is it something permanent? Well, we don't actually know yet. But scientists do know that in the past there were a bunch of other magnetic reversals. In particular, they count something like 183 reversals over the last 83 million years. That's a lot. But how do they know? Geomagnetic reversal evidence. Scientists have several ways to investigate past pole reversals, and one key method involves studying rocks and the behavior of magnetic minerals. When lava erupts from a volcano and cools to form rocks, it can preserve information about the Earth's magnetic field at that time. Certain minerals, like magnetite, act like tiny compass needles and align themselves with the prevailing magnetic field as the lava solidifies. This alignment gets frozen into the rock, creating a record of the Earth's magnetic orientation at that particular moment. As scientists them in layers of rocks from different time periods, they can see changes in the alignment of these magnetic minerals. If the alignment suddenly flips or shows a significant shift, it suggests a reversal of the Earth's magnetic poles. In other words, by analyzing the orientation and strength of magnetic minerals and rocks of different ages, scientists can construct a timeline of the Earth's magnetic history. Understanding these processes involves a combination of physics, principles, including of magnetism and fluid dynamics, to explain how the Earth's magnetic field is generated and how it can undergo significant changes over geological timescales. By studying the rocks and minerals on Earth, scientists can piece together the story of magnetic pole reversals and gain insights into the dynamic behavior of our planet's core. Over the past 10 million years, the Earth's magnetic field has flipped its polarity with remarkable regularity. On average, we observe 4-5 reversals per million years. During this time frame, these magnetic pole reversals are not uniform. They represent a rhythmic yet unpredictable cadence in the planet's geological symphony. The unpredictability of magnetic pole reversals adds an intriguing layer to Earth's geological history. Unlike clockwork, these reversals do not adhere to a fixed schedule or periodicity. In certain epochs, such as the Cretaceous era, the Earth witnessed prolonged stretches where the magnetic field remains steadfast without undergoing any reversals. This irregularity challenges our ability to predict when the next reversal might occur. Hey, before moving on, be sure to like or dislike the video so that we can approve it for you, the viewer. Plus, don't forget to subscribe to our channel by making sure to hit the notification bell. The weakening in the absence of a discernible pattern. Scientists rely on the concept of an average reversal interval to make sense of the magnetic flux. This average, calculated over extended periods, provides a statistical measure of how often these magnetic pole reversals tend to occur. So far, it seems they happen with an average frequency of 1 reversal every 450,000 years. But it's not always like that. For instance, the Cretaceous normal superchron holds the record as a period of geological time characterized by an unusually long duration of stable magnetic polarity, specifically normal, similar to the present-day magnetic field. This extended interval occurred during the late Cretaceous period, approximately from 83 million to 120 million years ago. During the Cretaceous normal superchron, the Earth's magnetic field remained predominantly in a normal polarity state for an extended duration, which is a rarity in the geological record. It stands in contrast to the more common pattern of shorter-lived magnetic intervals and frequent reversals. The reasons behind the prolonged stability of the magnetic field during the Cretaceous normal superchron are not fully understood. It remains a subject of scientific investigation and debate. As we already mentioned, measurements of the Earth's magnetic field have been ongoing since around 1840, with some records extending as far back as the 1500s, notably at Greenwich in London. Analyzing the trend in the magnetic field strength over this period reveals a consistent decrease. Extrapolating this trend into the future suggests a potential zero dipole movement in approximately 1500 to 1600 years. This declining trend is one factor leading some individuals to hypothesize that the Earth's magnetic field may be in the early stages of a reversal. Additionally, insights gleaned from the magnetization of minerals found in ancient clay pots indicate that the Earth's magnetic field was roughly twice as robust during Roman times compared to its current strength. Nevertheless, the present strength of the Earth's magnetic field falls within a range that, in the context of the last 50,000 years, is not exceptionally low. Furthermore, considering that the last magnetic reversal occurred nearly 800,000 years ago, the time frame for such events is not precisely predictable. Taking into account for excursions, temporary changes in the magnetic field, and acknowledging the complexities inherent in mathematical models of the Earth's magnetic field, the prospect of straightforwardly extrapolating to the magnetic conditions of 1500 years in the future becomes highly uncertain. The Earth's magnetic behavior is influenced by a variety of dynamic factors, and predicting its state over extended periods involves inherent challenges and uncertainties in the modeling process. Even the question, how quickly do the poles flip, is controversial. We do not have a record of any reversal, so any claims we can make are mostly on the basis of mathematical models of the field and are limited to evidence from rocks that retain an imprint of the ancient magnetic field present from when they were formed. Consequences on Earth. So, what impact would a magnetic pole reversal have on Earth, and could it pose a threat to life as we know it? The likelihood is extremely low, The Earth's magnetic field is encompassed within a designated space known as the magnetosphere, safeguarded by the solar wind. The magnetosphere deflects a considerable number of high-energy particles originating from the Sun and other celestial sources in the galaxy. However, it does not intercept all such particles, especially during periods of heightened solar activity, like solar flares and coronal mass ejections. In instances of solar activity, astronauts in Earth's orbit might require additional protection to avoid increased radiation exposure. This emphasizes that the Earth's magnetic field offers only partial resistance to spaceborne particle radiation. Interestingly, the magnetosphere can even accelerate high-energy particles at the Earth's surface. Our atmosphere acts as an added layer of defense, blocking all but the most energetic solar and galactic radiation. In the absence of a magnetic field, the atmosphere would still effectively shield against most radiation. In fact, the atmosphere functions as a protective barrier, equivalent to a concrete layer about 13 feet thick. Over the course of millions of years, humans and their ancestors have experienced numerous magnetic pole reversals, without any clear correlation between these events and human development. Similarly, patterns of magnetic reversals do not align with historical patterns of species extinction. Certain animals, like pigeons and whales, rely on the Earth's magnetic field for navigation. If a reversal unfolds over thousands of years, spanning many generations for each species, these animals may adapt to the changing magnetic conditions or develop alternative navigation methods. Hence, the overall impact of a magnetic pole reversal on life on Earth appears to be minimal, and the planet's living organisms have historically demonstrated an ability to adjust to such changes. As we comprehend, magnetic reversals can spontaneously occur as a self-induced process. However, it may surprise you to learn that these reversals could potentially be influenced by external factors like meteorite or comet impacts. Yes, you heard it correctly. Although highly improbable, there exists the slim possibility that an impact from a meteorite or comet, or even a more subtle event such as the melting of polar ice caps, could act as a trigger for a reversal in the Earth's magnetic field. That's all for this video. Thanks for watching.